So almost done grading. So we should get your marks out to both the group and everything else up on Canvas definitely this week, Friday at the latest, ideally by Wednesday. So far, you guys did very well, actually. Do not worry. Second thing, too, if you haven't seen already, on Piazza, I have opened a voting for group names. You guys killed it this time, so I had to make up two different points. So there's a group of six, a group of six. Please choose your best. We will announce those on Friday. This week, we have a TA tutorial today. Next Canvas quiz will open on March 22nd. Again, due in 1 week. One quick reminder, there'll be no in-person lecture this coming Monday. So 1 week from now, no in-person lecture. Ideally, we should have no lecture to cover at all. Worst case, there may be a couple things I might do as a video just to top up or review any parts of Fridel-Crafts that we cover this week. There will still be a TA tutorial on that Monday, though. So last class, we left off introducing aromatic substitutions. This is our first example of taking benzene and using it as a nucleophile, which feels weird because it's a super stable molecule. We have to interrupt aromaticity, but there's kind of two things that make this possible. We're using the high electron density, all those 6 pi electrons as our nucleophilic center. We're only allowing this to happen if we have very, very, very extraneous electrophilic species. So nitration, sulfonation, and halogenation are not being done with your run-of-the-mill electrophiles. These are specialized electrophiles that are usually formed by some sort of a sequence of increasing the reactivity in the reaction. As I discussed last time, each of those compounds, usually what we're going to do is start with the reagents. We're going to generate this powerful electrophile, use it right away, which only temporarily interrupts the aromaticity of the reaction. We get it back through the loss of a proton. So, your Greek question. This is a deep cut. What happens to this material if you treat it with zinc, mercury, HCl? Yeah, sounds familiar, right? Okay. So these conditions, does anybody remember the name of this reaction? Not Wolff-Kishner, it's the other one. This is Clemmensen. Remember, we have two different reactions, Clemmensen, Wolff-Kishner. They are both reduction reactions. What do they do? What does Wolff-Kishner do? It reduces things, but what does the starting material product? Yeah.
It gets rid of the carbonyl while also providing an acid just in case there's a protected group.
In this case, yeah, it's a way of deleting a carbonyl under acidic conditions. Wolff-Kishner is deleting a carbonyl under basic conditions. Those are your two ones. The goal here is to surgically target that. And ideally, it's not going to touch any other part of the molecule. We didn't talk about the mechanism. It's some black magic radical process. But it allows us to replace carbonyls with hydrogens. So it's a way of reformatting a molecule to get rid of that one. Now, this is going to come up today. We're going to use this one, and the whole reason we've got the Clemmensen and the Wolff-Kishners for some of the reactions we're going to talk about today. So last class, we were introducing electrophiles where there's halogens, nitro, sulfonate. This class, we're going to talk about carbon-based electrophiles. This is what we called Fridel-Crafts alkylation, acylation, and then a quick introduction to how these rates work. Now remember, alkylation means adding an R group where you have things like CH2R. We're adding this fragment. Acylation, remember this is nucleophilic acyl substitution. It means adding a carbonyl R group. So the difference between them is, saturated sp3 carbon type additions, what we refer to as alkylation. Acylation is the addition of a carbonyl and stuff, right? So it's a different oxidation state at the center that we're actually adding in. So these are the electrophiles that we get to use here is what makes this happen. The fundamental mechanism, as far as the nucleophilic substitution, is really the same. You still have a benzene. You still have to interrupt the benzene by using it as your nucleophile, and you still need to increase the electrophilicity on whatever the other fragment is to use benzene in this way. It will create that intermediate complex where you have that sort of delocalized carbocation where the loss of the proton gives you back your aromaticity. So the basic form that we've seen up until now is the same reboot. The difference is alkylation and acylation is what type of electrophile we're going to use to get this to happen. So the chemistry is the pairing of what we use to access this. So first, alkylation is how we put and stitch a carbon-based group onto simple benzenes. So replacing a carbon hydrogen with something like this. Now to make this happen, again, if you just took a simple alkyl halide, alkyl bromide, benzene is not nucleophilic enough to react with a simple alkyl halide on its own. We have to introduce catalysts, just like we did last time, and these are going to be Lewis acid catalysts, not protons, because the job here is to activate that chlorine to turn it into a phenomenal leaving group, into something that's like a carbocation effectively, that then baits the nucleophile into the benzene in this place to do that coupling. So just like we talked about with our other ones here, the first step is always going to be increasing the electrophilicity. It's taking the alkyl halide we have and ramping it up in order to make it way more reactive to get these reactions to kick off. Otherwise, you can mix these two all day, nothing will occur. So the mechanism we use here follows what we did with bromination. Remember, in bromination, we started off with FeBr3. In this case, you typically match some kind of a metal, so it's either iron or aluminum in the middle here. Those are your two choices, and you can choose either, doesn't matter. You have sort of this option to use some type of a like a +3 kind of species. In this case, this is aluminum 3. Iron would just be your iron 3 complex. You use a metal in the middle, and you're pairing it with whatever halogen matches the leaving group of choice. So if you happen to be using alkyl chlorides, you would typically use aluminum trichloride or iron trichloride. If you happen to be using an alkyl bromide, you would use aluminum tribromide or iron tribromide, right? The reason why is that we just don't want to mix reactivity. As this reaction occurs, you're going to be stripping out chlorine from the reaction, and we just want the catalyst to be basically consistent. Whatever the X ligand is, or the ionic part of this ligand, we match it to whatever the leaving group is so there's no changes as the reaction is running. It's basically going to be consistent. So how this reaction works, if you had to guess, remember, aluminum or iron, when it's in this tri-state, this goes all the way back to, in this case, it's a direct replica. Remember when we talked about dibal? Dibal is a neutral trivalent species, 1 hydride and 2 carbons, right? This is a neutral trivalent species where you have 3 chlorines. Like we talked about the polarization, this is an aluminum 3 in the middle. Each of these is sort of a -1 ligand around the outside. So you can think of it as a very electropositive metal in the middle. Being that it's neutral, this, if you had to think of the sort of the hybridization, it's kind of sp2. It's trigonal planar. It's got a vacant p orbital that's going to attract your lone pair. So it'll coordinate in the same way that something like dibal, first move in dibal, was to coordinate onto the carbonyl to make this negatively charged species, positive on the carbonyl. So you're polarizing that bond. Here, because we have a sigma structure, the complex we're going to form is still kind of this chlorine, and I'm going to put a dotted bond to aluminum, Cl, Cl, Cl. Now, when you do this, you're taking the very electropositive aluminum, you're coordinating it over. If this was a true bond, if we actually look at this as a bonding structure, like this, that would put a negative charge around the aluminum center, and effectively a positive charge over here. What you're doing is grabbing onto that halogen. It's a source of a lot of electrons in the lone pair. The aluminum or the iron would coordinate into that and basically tug on that chlorine. As a result of doing that, it's going to pick up a negative charge itself. It's not oxidizing, so the aluminum 3 now has more X ligands around it. By doing that, you're fracturing or fragmenting this bond right here. So the way you can sort of think of drawing this is kind of like a dotted bond across here. This would probably be described as a delta plus and a delta minus. It's forming this charge as that bond is stretching. The final complex, you can imagine it as, so if this was a transition state, the final complex we're making here is the carbocation and Al, Cl, 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 Cl minus, the fully ionized one. And we can treat it as this carbocation where you have this aluminate, this tetracoordinated species, nearby just to balance out charge. All you're doing here is by using these Lewis acids, grab onto a center of a lot of electrons, pull on that center and effectively ionize it. This is the same thing we see with SN1, right? If I'm trying to make an oxygen, water, into a good leaving group, I protonate it first to make it into a better leaving group. Similar thing here. Chlorine is a good leaving group. If I want to ramp it up, I'm going to grab it with my aluminum, haul on that center to leave behind a positive charge. So it's a way of making these carbocation type centers, and it really has the same reactivity and disposition as your normal carbocations. Their stability, their ability to migrate or do anything else is the same thing we've seen before. So the overall mechanism, you can think of it as I'm transferring it. You could draw this as a localized zwitterionic structure where what you've done is use some of that lone pair on chlorine to donate to the aluminum. Aluminum picks up a negative charge as it forms that bond, leaving a positive charge on the chlorine, which then fractures into the aluminum tetrachlorinated anion and the carbocation. So it's the halogen and Lewis acid equivalent of an SN1 reaction. Next step, once you've made this carbocation, this is now your powerful electrophilic species. You've made a high concentration of this where the aluminum is happy with its 4 chlorines. It's over in the corner, does not play anymore. Now the mechanism follows what we've done before. Capture to form a carbocation. And why this is going downhill is we start by making this secondary carbocation, very, very, very electrophilic. We're going to borrow that aromaticity to make a stabilized carbocation. Remember, we can draw this. Its sort of resonance form is going to be each of the resonance isomers where we delocalized around this ring, and then plus the third one where it's actually at that point. So the carbocation here that we generate is going to have positive charge at each of the ortho and para centers. Last one. Like this. That's our intermediate. All we have to do to close it is any of these protons. We're going to have a base. We'll pick off this and regenerate our aromaticity. What's your base here? Probably. What's the piece that we're not showing when you show you that carbocation? It's aluminum tetrachloride, right? Probably. The basic species here is going to be your Cl, aluminum, Cl, Cl, or whatever reagent you chose to use here, which means when this reaction's done, I've got HCl and aluminum trichloride. Once we protonate that structure, you can think of it as somewhere on the continuum. Oops. Thanks, TAs. I mean, that was totally on purpose. That one. Thank you. Do not grab the sp2 proton. So this is usually used, we use the metal as a catalyst, which means by protonating back that last part, you're generating HCl. That can go off as a gas. That's less coordinating to your aluminum, and it frees up the aluminum trichloride to go around one more cycle, deprotonate or grab a chlorine from your alkyl fragment, and then continue this process. So, ChemDraw mechanism. Think of that first step as our activation, just our generation of our carbocation, just like SN1. Once we've got the carbocation, it's electrophilic enough, can be attacked by the benzene. That gives you your intermediate, where you have your acidic proton on the sp3 center, where deprotonation of that gives you back your aromatic ring, gives you back your catalyst, because you're basically protonating back your HCl effectively as you do this. On workup, all this stuff breaks down. Water would be introduced. You'd break this back to your aluminum hydroxide and your HCl components as well too. Usually be doing this with base to try and mop up that proton as well. So something like bicarbonate or something. So we're going to discuss this through. You can use this as a way, assuming what we call just monosubstitution. Benzene plus any of these halides, where you're matching it against some type of a catalyst, produces your carbocation to get the reaction to add. So in the end, though, you're playing with carbocation chemistry. Fridel-Crafts was very, very important because it allowed us to take very simple petroleum-based aromatics, benzenes, toluenes, and functionalize them. You could build up these large carbon fragments. So it seems like it's magical in the sense that, okay, we can add these carbon fragments anywhere we want. Again, there's rules of directions and where we go, but super powerful because it takes raw building blocks and builds them into these larger fragments. The problem is, it really only works with secondary centers. If you try to go through and did this with primary carbocations, it does not work well with primary halides. Why do you think? What do you remember back about playing with carbocations? What's the issue with primary carbocations? They're super, super unstable. So the same conditions here. Now this is where we have a tipping point where if we try to generate a primary carbocation and the conditions are not so harsh, it just chooses not to exist. Something like aluminum trichloride is powerful enough, it will make it exist. It's just the problem there is it will very rapidly rearrange. So there's a tipping point with any of these highly stabilized or highly unstable sort of structures. If we're talking about something like, okay, yes, primary carbocations are bad. Generally, we avoid forming them. Something like aluminum trichloride or iron trichloride is powerful enough that it will do that even in spite the fact that the primary carbocation is terrible. It just leaves the molecule with no other choice but to deal with or otherwise rearrange that primary carbocation. So this goes back to what you guys have seen, like carbon shift and hydride shifts. Migration of your carbocation after it's been formed is faster than any reaction you could possibly have. So if I took a molecule like this where my intended target was I want to stitch this carbon fragment, my goal was to take that center and stitch it onto my ring because my target, I wanted to take benzene, I wanted to add that carbon and have this branching fragment like this. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. I really wanted the substitution to have this, this primary center being the point of junction. This is important for simple molecules we've always like ibuprofen. Ibuprofen has very simple primary substituents like this onto benzene. So this is a very common type of a junction we have for a lot of different med chem targets. The problem is you will not make this one. In the process of putting these two species together, again, the catalyst is powerful enough that it's not a choice. You're still making that carbocation. It's just as soon as you do, the molecule will look around. And if you have any way adjacent to that center to allow us to migrate that carbocation to make a more stabilized carbocation, that will happen. So very, very, very fast, we make the tertiary. So it's a 1,2 hydride shift, effectively. The molecule will rearrange to give you this stabilized carbocation, again, because the Lewis acid we've applied here still is powerful enough to make it. It's just that the intermediate that you've generated is not stable enough to be retained for the reaction. Once you've made this tertiary carbocation, now the benzene can get involved. Tertiary carbocation is still electrophilic enough to engage. You will still make a product of this one. It's just the substitution pattern will be not what you hoped for. So it will add to, oh, sorry, I will recolor it. This red center here is what we're going to add to. Which would have been that one over here. So the advantage is we now have a way of taking simple halides, sp3 centers, and stitching them onto the ring. We can make carbocations reliably this way. Downside is the relative stability of the carbocations is still something we can't escape. If we make a primary carbocation, the molecule will look around and actually do anything that's possible to do this rearrangement. Now this even applies with simple linear structures. Even if I had like a linear butane, making a primary carbocation will immediately rearrange to my secondary center. Yeah?
If it has a secondary center and a third, like
tertiary center?
Option, would it rearrange in like both ways so there would be a mixture of what happens?
Exactly. This is exactly it. Typically, your tertiary center, if you can access one, it will rattle around to find that one. If a molecule has immediately adjacent to it, let's say you form it at a primary, it rearranges to a secondary. If it goes to another one, it makes it to a tertiary. If it keeps zipping down the line, it will continue to do that. So the thing we're trying to emphasize here is the conditions we've applied here stabilize the formation, well, not stabilize, they allow the formation is the best way to say of carbocations. As soon as they're formed, every one of the things that you learned maybe in 203, 233 for carbon migration, ring opening, hydrogen things, those are all in play. So anything about carbocation rearrangements can occur here. So the disadvantage of this step is you kind of make a mess unless you know exactly what type of conditions you're applying. You will make multiple products this way, absolutely. So we'll discuss this part through. Draw the mechanism. This is a case where if I tried to do this with this primary, this becomes our major one too. So showing through the actual full mechanism, the benzylic intermediates, and the carbocation migration. So this is the limitation. First off, the halogen must be attached to an sp3 center. This really only works for making molecules like this, secondary or tertiary, where the center we're attaching here is an sp3 carbon. So Fridel-Crafts is our first way of decorating these aromatic rings with these simple carb things. If you needed to make a tertiary center, this is a really good way of doing it. Funny enough, at that time, vinyl centers, aromatic centers, like if I tried to make something like this, double bond, where I have an sp2 junction, or bi-arrows, like this, these sp2 junctions, these are not possible using Fridel-Crafts. There's actually a much better way that only in the last 10, 15 years we've gotten very good at that actually makes the whole Fridel-Crafts things, nobody go anywhere near that reaction anymore. These sp2 couplings is what's called Suzuki couplings or cross couplings. And it's a phenomenal way of doing it. Different mechanism totally, but you cannot access these ones through this primary carbocation type reaction mechanism. The other thing about this too is it installs alkyl groups on activated rings. Now remember we talked about this before. If I took benzene and I put nitro on it, what do you think it does to the relative nucleophilicity of benzene? Start with benzene, put a nitro on it. Is that ring as nucleophilic or less nucleophilic than you started off? Yeah, it's an electron withdrawing group. So Fridel-Crafts works, but it only works with relatively activated centers. If you already have a nitro on there, even having that one nitro on and forming a carbocation, it's not as nucleophilic. It's actually not nucleophilic enough to decorate anymore. You can do it with benzene. You can do it where there's electron donating groups on benzene, but you very easily can shut down the ring. So Fridel-Crafts is right on the edge of formation. And really, there's two problems with this. One is I have to take my benzene. I need to have it relatively nucleophilic, so think simple things without electron withdrawing groups. If I do this reaction where I have an alkyl halide and I put aluminum trichloride in, I've made this bomb of carbocations. They will go find lots of other things to do if the benzene is trying to sit there and even hesitate and like, do I really want to engage? I got this nitro. Do I really want it? Too late. Reaction's over. Carbocations made the decision for you. Nothing else can happen. Yep.
In a situation where synthetically we are using this reaction and it future product as an output?
If you had to, if you're trying to use this in synthetic strategy and you have no other choice where you make both, it is totally fine to say, I'm going to use the minor, I will isolate that minor, and then I will go do things with that one if you're suggesting a strategy. It's not very efficient, but it may be the only move you have at this time. Absolutely. But what this just means is you have to choose. This activation problem means the types of groups you put in the molecule, the sequence at which you do the reactions can be something we're going to focus on. So you can do nitration, sulfonation, Fridel-Crafts, but the order that you do them will preclude which ones will work or not. We'll talk about that one a lot later in this week. The other thing too is polyalkylation. What did we say an alkyl group was? Is it an electron donating group or electron withdrawing group? Just simple things like methyl, ethyl. They're donating. Remember, a ketone is less electrophilic than an aldehyde because two alkyl groups are donating into that carbocation, or to the carbonyl center. So what happens here is, unlike nitro groups, where you add one and it shuts the system down, it calms it down, here I take benzene, I react it, now I've got an activated group, which means the second one is easier. So polyalkylation with Fridel-Crafts is a problem. If you're going to stitch in a group, it's really hard sometimes to stop at one. If I was to go back and make this product, that donating group, or sorry, this product here, the donating group here is going to activate my ring for another functionalization, and another, and another. So keeping control of this is something that's a bit tricky. And finally is this one here. Primary halides, not available. So certain substitution patterns are not going to be something we can access. So because of all this, because of how we have these other points, there's the other way to stitch in carbon fragments, and this is where we use acylation. So alkylation, very simple, works great to install tertiary centers. Downside, you may add more than one. If you really want primary substitution, if you want control, we use acylation instead. This is a way of getting around all those other problems by forming a different kind of intermediate that then has this carbonyl in there that we can deal with. We can reformat that part later. So here, we use the same type of activation, it's aluminum trichloride, and we're going to start with acyl chlorides, acid chlorides. So it's a higher oxidation state. What we generate here is a different electrophile, but similar, oh my gosh, today is one of those days. It's similar in form as what we've had before. If I was to do this addition, oops, I'm going to draw up my chlorine, my new bond to my aluminum, I'm going to have a positive charge resident here, negative charge on my aluminum. I would then eliminate this to give you R double bond plus and your aluminum tetrachloride. This guy, you can think of it as resonance stabilized. Like this. This is what we call the acylium cation. It's related to things like our nitro cation, positive nitrogen. This is a positive at carbon kind of center. Very powerful, very good electrophile. And again, it's just generated in the same way that we did with our acyl halides, but it comes from, alkyl halides, it comes from our acyl halides. So this is where you take your carboxylic acids, SOCl2, generate your acid chloride, and then activate it this way to get us our carbon equivalent at this higher oxidation state. This gives us a couple of really good things. Now that we've made this, these are still very, very positive at carbon, but remember, what did we do with nitro? The reason that we use nitro is we install nitrogen on a ring, it's this high oxidation state, but we would typically, the next move we would do with nitro is we reduce it. We're using the high oxidation state of something like an NO2 group for the reactivity. It allows us to install it onto a ring, but then if we go through and do a reduction, cleave those nitrogen-oxygen bonds, I can reformat it back into NH2, like an ammonia. Similar thing here. I can take advantage of the fact that if I had benzene plus this acylium center, I can now add benzene to my carbon. It's surgical. There's your carbon plus, and these do not rearrange. So if I happen to have something like secondary centers nearby, it's going to stay resonant on this carbon. I'm not going to see carbon migration. I'm not going to see proton migration because this at least is a resonance stabilized super powerful electrophile, which means it stays put. I can decide where I want that group to be. So it adds my acyl group on to give you your carbocation, where once again your aluminum tetrachloride anion is going to be your base to return your proton. And it gives you HCl and aluminum trichloride. So this solves a bunch of problems. First off, if I form this carbocation, it's like I formed it at a primary center. It's the end of a chain. Wherever the carboxylic acid is where I can add. So it doesn't hop around on me. Second problem, also solved, that is that deactivated or activated? If I have a carbonyl next to the ring, am I withdrawing or donating? Remember, this is going to be, this center here is delta plus. So this is an electron withdrawing group. It's kind of like nitro, not nearly as powerful, but it means I can add one of these groups and I don't have this problem of polyaddition. I'm not dumping more electron density into my product. I can add one and it will stop. So the good news is I've solved those two issues. Positionally, I will only ever add wherever this carbon happens to be. It doesn't hop around on me. Second, the product I make will not add multiples. It's a lot easier to control. So the acylation is great in terms of adding carbon fragments and giving you back your selectivity and control. So if your product that you're trying to make was one of these primary kind of centers, acylation is a better choice just in terms of adding that center. The downside, though, is you've got this stupid carbonyl here, right? So great, what we did is we used reactivity to add this carbon in. We get our selectivity back. We add only one of them. But it's not, let's say if I really wanted a benzylic CH2, I have to deal with this, this center. And that's where Wolff-Kishner and Clemenson matter. If I form my product where I've done an acylation reaction, it leaves behind this ketone that I don't want anymore. I only used it to add that center directly to this ring without polyaddition. And after it's installed, I'm going to go through, use my reaction conditions to replace it, to delete it. So this is in the same way as kind of back, I think we've used this strategy a couple times now. When we did amine synthesis, using Gabriel synthesis, I can take a nitrogen that's not very acidic, put a whole phthalimide around it, now I can deprotonate it, now I can do nucleophilic addition, then I cut off that prosthetic group. With nitro addition to my aromatic, ammonia is not going in there, it's not electrophilic enough, but the nitro is, I could do the reaction, form my carbon-nitrogen bond, and then delete out the oxygen surrounded by reduction. Similar thing here. If I really want this primary kind of center, I can't go at it directly. I'm going to do this end move around it. I acylate it and then reduce it. So you're picking up two steps. It takes more time, takes more energy, but it's a circuitous path to a target where the direct energetic path would not work. I can't do a direct acylation for one of these reactions necessarily, so I use something like this as a two-step process to give me back my selectivity. There's another advantage that Clemenson, generally it works really well to give you these benzylic ketones, to give you benzylic centers. So this is partly why the Clemenson reaction was formed, is acylation. Fridel-Crafts acylation is a pretty good way of installing a carbon where we want, but then we have to go through and delete that carbonyl. So the Clemenson reaction is a great way to replace it with our CH2, to give me back your benzylic centers. So this is where we use these two in different ways. The acylation is a two-step process where we use reduction at the end of this, and it gets around this whole problems that we normally see with primary centers. Again, use it where it makes sense. It's not a universal where both of them are going to be directly comparable. This takes more steps, but it gives you strategic access to monoaddition and primary sort of centers. If polyacylation is not a big problem because of whatever's decorated the ring, Fridel-Crafts might be a perfectly good choice. You may have an aromatic ring that there just really is nowhere else for it to go, in which case Fridel-Crafts is a totally appropriate one. We're not saying never use Fridel-Crafts, just use it where it's appropriate. Nothing is a direct hammer. Okay, so what's the product here? If all you did was take this molecule and aluminum trichloride, what do you make? Okay, let's go slow. If you add this catalyst to this acid chloride, remember also, where might I get this acid chloride? What's the fastest way to generate this acid chloride, or what precursor would I need to make this one? Yeah, SOCl2 and the carboxylic acid, right? That's probably where this would generate from. Can anybody think of where that carboxylic acid would come from? Yeah, we'll do that later. So this is going to be generated from carboxylic acid, SOCl2, right? That gets us to this guy. All right, now we have the acid chloride. We're going to use aluminum trichloride to generate my acyl carbocation. So you can think of that as double bond O plus and aluminum trichloride minus. Now what? If this is all you have, there's nothing else in the situation, nothing else given to you, what are we doing? Probably. Yeah, this is where count to 5, count to 6, right? If I have my nucleophilic center, let's take that one, 1, 2, 3, 4, 5-membered ring. It's a ring closure across here. Does it matter which center I use? Like, what if I use the green center? Is that a different product? No, it's symmetric, right? Green versus blue, identical. Do you think I should make, let's say, red center? What's wrong with that? Yeah, this becomes bicyclic, right? You're trying to cross-conjugate, reaching across the ring. So it's those ortho positions here that you're going to use as your nucleophile. If we had to try and cross across the ring, that gets hard. Again, if you, the rule with a lot of this stuff, if you build the model kit and the model snaps as you're trying to make it, probably not what you should be building. So, the intermediate you're going to generate, you're using that carbon center as your nucleophilic center. You have your H, and we have a 5-membered ring appended to the outside. So I'm going to draw it like that. And if we count these off, 1, 2, 3, 4, and 5 is 1, 2, 3, 4, and 5. Carbon 1 is bonding to carbon 5. Carbon 5 still has carbonyl attaching to it. Last step. Aluminum tetrachloride grabs that proton, returns the double bond, and we get our product. Like that. HCl and aluminum. So these reactions are still phenomenally useful, some of the most important industrial reactions we have, because it allows us to surgically reformat these aromatic rings. As soon as we do this too, and we build up these kind of structures, it's amazing how much the functional properties of these aromatics change. It allows us to make them and separate them quite easily. So we've got 2 other discussions that we're going to do after. If you had to try and make this one by Fridel-Crafts, why it might work, is acylation better? And then finally, proposing a route to something like this. This is where we bring together targeted functionalization that we're trying to do using either. The last thing, what we're going to bridge over to now, is these are our primary electrophilic reactions: nitration, sulfonation, halogenation, and carbon formation. So alkylation, acylation. Those are our points. Now what we have to do is optimize which reaction we're going to use for what kind of step. And this is where it comes back to look at the individual substitution patterns, look at the types of molecules that we're building, and we've got this rank order of basically what happens to the products in terms of activation or deactivation. So let's say I want to make this transformation happen faster. I want to make this product better. What are the things that you think you can do? What are your handles you have to make this quicker? So this is totally go to the lab and everything else. What are the things that you have available to you to make any reaction faster at all? Forget about this one for a second. What do we normally do? Heat? Great. Beat the crap out of it. Yep. What else? High concentrations? Yep. That's our rate equations? Yep. What else? Catalysts. We're already using a catalyst probably. These things like aluminum trichloride. If we want to change at the substrate level to make something faster, remember, what did we say that these diagrams looked like? If I drew the energy level diagrams for this, I'm starting off with relatively stable starting materials, right? These are my aromatics. Let's say I've already got my super highly activated system, right? So forming that Y minus, I could potentially increase the concentration of my Y plus, my electrophile. So finding conditions that jack up the concentration of my electrophile, that can help me. After that, I'm going to some very, very, very high transition state to get to the sigma complex, which is up here at this intermediate, and then we come back to our product. So anything I can do to stabilize that carbocation relatively will help me. And what's different about this than compared to normal carbocations is the positional distribution of where those positive charges sit. This intermediate at the ortho and para positions specifically are delta plus. It's not at the meta position. So the distribution of where that positive charge is not uniform over the entire benzene ring. It means if I put groups specifically at the ortho and para position, I can help or otherwise stabilize the developing charge we have here. This is kind of like we see with SN1 reactions. Anything that can stabilize that positive charge that's available will help me out. Which means, what do you think would happen if I'm trying to substitute that center right here, but I'm going to change my starting material, so that's that center. At this center right here, I'm going to put a nitro group. Did that just help me or hurt me? So is a nitro group a donor or withdrawing? Withdrawing. If I have a nitro group on that pink center and I'm trying to substitute the blue one, this is a bad move. My intermediate that I'm trying to do by this substitution would place a positive charge right next to that nitro group. So I don't want to do this. That would hurt me. That would generally increase the energy level of my intermediate, slow the reaction down. Instead, what if I put something like OME? Remember back to carbonyls. Ketone versus ester. What is more electrophilic, a ketone or an ester? Ketones. Because remember, ketones, methyl, methyl versus methyl carbonyl OME. If I have these lone pairs act as pi donors. They're donor groups back into that group, and they end up tamping or otherwise stabilizing the charge we have here by resonance, right? The lone pair is donating back into that center and makes it easier. Similar thing here. The carbocation I would generate at that center is sp2 hybridized. The lone pair can donate into that center. This is going to help me out. If I was having an OME group at this position, it will act as a pi donor, which will help to stabilize the carbocation that's available. It should lower the relative stability of that one, and it'll help me to accelerate the reaction. So this is where we're going to kick off at next class, is how we use different groups in different positions in order to otherwise activate or deactivate the ring. Yeah?
Okay, what's up, guys? All right, so we're going to talk through the mechanism to make each of these products, as we mentioned, talking through why this becomes our major product. So in this reaction, first thing we're going to do is we have to make the electrophile. So with all of the aromatic substitutions, we have to create the electrophile that's going to be responsible for this reaction first. So we would draw that out as our alkyl halide. In this case, it's our propanol chloride, chloropropane. And we have our aluminum trichloride. So we're getting a Lewis acid connection here. You can draw this as like a coordination complex initially, where we have a formal bond between these, where we now have a negative charge on our aluminum due to our formal bonding arrangement, and positive here, which then fractures to give you a primary carbocation and our anionic aluminum. So this is our electrophilic species against non-coordinated or an outer sphere ion with this piece here. And this is going to exist very temporarily in this state. So you can imagine that you have a small population of this primary chloride. Now, it's a lot easier to take the hydrogens adjacent to it and rearrange them. So this will undergo a very rapid reaction to produce a rearranged secondary center. And I'll talk a little bit more about the mechanism for how this happens, but effectively think of it like, remember, the carbocation itself is an sp2 center with a vacant p orbital here. That p orbital is partially stabilized by hyperconjugation of both the carbon and the hydrogens, the sigma bonds adjacent to it. As a result of that, some of these bonds here are donating some of their electron density to that center. So very transiently, you can imagine that the hydrogen, kind of like the bromonium you've seen before, exists like this. So it's a partially broken, partially formed bond out to this primary center. And the reason we make the secondary one is just on the energetic diagram. The primary carbocation will be much higher in energy. The secondary is at least lower in energy, so there's a thermodynamic driving force to create the more substituted center. So that's one way to think about the mechanism this is happening, is it's a rearrangement from the primary to the secondary to make a compound more like this. Now that you have this, you have a high concentration of the more stabilized one and a low concentration of this one. So it depends on which one of those two carbocations the benzene is going to see. If you imagine a mole equivalent of this reacting, you could say something like one of these, or 1 time out of 10, it'll be the primary carbocation, and 9 times out of 10 would be the secondary. So we'd expect something like and these are just numbers for illustration, 9 to 1 might be the ratio we'd expect, but it really comes down to the stability of these two. So if we were going to capture the primary carbocation, we're going to make this guy, and then the base picks off that proton and closes. Excuse me. One more carbon. Oh, no, that's right. 1, 2, 3 makes 1, 2, 3. Sorry. So the new bond we formed is this one right here for 3 carbons. And that gets us our minor product. Again, there's not going to be a lot of this around. Most of this will rearrange. So the other product, the major product, comes from the same mechanism, except the attack will be on the rearranged carbocation, the secondary, where we end up with our secondary sigma complex, which then is going to form our product, our major product over here. So once again, the actual electrophilic coupling step is exactly the same we've seen before. It's the formation of the sigma complex and then a deprotonation. The nature of the electrophile is what really drives which one of our products forms as major minor. It may initially form the primary carbocation, but rearrangement is going to help to form the more stabilized one. So for this one, we're treating our electrophiles with our catalyst. Those are going to generate the corresponding carbocations. So in the first case, we're generating the secondary carbocation, secondary case. It's tertiary center. So both of those are electrophile. We're going to do a coupling reaction where we bring together those two fragments like this. And in the second case, our aromatic ring is going to be substituted at now the tertiary center like this. So in both cases, the carbocation that we generate at the corresponding center is just coupling to the aromatic ring as our fragment. Okay, so we're giving you a molecule that is impossible to make either by alkylation or acylation. So let's take the alkylation one first. If you imagine working backwards, if we tried to make this, we would use benzene as our nucleophile. And if we're fracturing this bond, that means we're trying to make it from something like this guy, this positive charge over here. So that you might think comes from the carbocation that you could generate here. That's not the problem. Like it could come from, let's say, that chloride. The issue is in the stability of this molecule. Remember, if we have the ability to do a migration, either a proton or a carbon, to make a more stabilized carbocation, it will. So this secondary carbocation has a quaternary center next door. If we have a methyl migration, it will generate a tertiary carbocation like this. So this tertiary carbocation would be the major thing that actually couples. So this is an issue, or trying to do alkylation to make it is really just the fragment we've tried to make, and the carbocation we're trying to make happens to be related to a much more stabilized carbocation that we'd have to generate. So this route fails just because we can't access the electrophile we're trying to form. Now, for acylation, the problem there is a little bit different. Remember, for an acylation reaction, let me just show you a generic one first. We take an acid chloride to make our Fridel-Crafts acylated product like this, which we can carry forward and do the ketone reduction right into this. Now notice acyl chloride, which already has 1, 2, 3, 4 bonds, produces a ketone product, 1, 2, 3 bonds here, where you've got that fourth R group. And then we reduce it to make a benzylic center with 2 protons. It's a primary center is what we result in. And unfortunately, because of the acid chloride, that is the only substitution pattern that's allowed. The acid chloride that you need to start off the reaction is at a high enough oxidation state. We've already got 3 bonds tied up in the acid chloride part, which allows only 1 R group to be attached to the carbon center that we're bringing to the group, right? This is the only product you can make, is these ketones. If you look at your starting material here, that center has 2 alkyl groups. So hypothetically, you could say, well, that would come from something that might have to look, right? It's going to be an acyl, and I want 2 R groups on here, 1, 2. That is a Texas carbon, right? That's over-hybridized. So the limitation of the acylation reaction is you can really only produce these primary centers. They're very selective. This has all the other benefits, but these high substitution patterns are not possible from acylation. So if we had to make this, if this was our target, as we discussed before, this linear one, or formation, whenever you see a primary center like this is not from Fridel-Crafts alkylation, because the primary carbocation that we would need would rapidly isomerize to a secondary. So we couldn't generate this. Instead, what we'd probably do is take our acid chloride, in this case like this, and aluminum trichloride. That would give us our ketone product. We can carry that through one of the deoxygenations, so our zinc, mercury, and acid will give us our Clemmensen reduced product here.